In a universe so vast it's beyond human comprehension, filled with billions of galaxies, each teeming with countless stars and potentially habitable planets, a profound silence echoes. This silence poses a question that has puzzled scientists and philosophers alike. In this immense cosmic expanse, why haven't we found any evidence of extraterrestrial life? This enigmatic question, known as the Fermi Paradox, invites us on a journey through the complexities of astrobiology, the mysteries of cosmic evolution, and the depths of human curiosity about our place in the cosmos. The Fermi Paradox grapples with a high-stakes question in the realm of astrobiology and astronomy. With the vastness of the universe, why haven't we found any clear evidence of extraterrestrial life? Named after the Italian-American physicist Enrico Fermi, the paradox arises from a contradiction between the lack of evidence for extraterrestrial civilizations and various probability estimates for their existence. Fermi, known for his work on the Manhattan Project and his contributions to quantum theory and nuclear physics, casually posed the question during a lunchtime conversation in 1950. While discussing recent UFO reports and the possibility of faster-than-light travel, Fermi suddenly asked, "Where is everybody?" This simple question encapsulated a complex issue. Given the age and size of the universe and the likelihood of Earth-like planets, it seems improbable that we are the only advanced civilization. Yet there's a conspicuous absence of contact or evidence. The Fermi Paradox holds significant importance in the fields of astrobiology and the search for extraterrestrial intelligence, SETI. Astrobiology explores life's potential in the universe, considering the conditions and processes necessary for its existence. The paradox challenges astrobiologists to reconsider assumptions about life's rarity or commonality in the cosmos. For SETI, the Fermi Paradox shapes search strategies and expectations. SETI initiatives, involving the scanning of the skies for signals from intelligent extraterrestrial sources, hinge on the assumption that such civilizations exist and are attempting to communicate. The paradox poses a conundrum for SETI researchers: how to reconcile the great silence in a seemingly favorable universe. The universe's immense scale and age are at the heart of the Fermi Paradox. Current estimates suggest the universe is about 13.8 billion years old, with about 2 trillion galaxies, each containing billions of stars. This vast expanse and the long timeline provide ample opportunities for life to arise and evolve. The sheer number of stars implies a high probability of planets orbiting them. Recent advances in astronomy, particularly the use of space telescopes like Kepler, have confirmed thousands of exoplanets, many in their star's habitable zone where conditions could support liquid water, a key ingredient for life as we know it. This abundance of potentially habitable planets strengthens the paradox. If Earth-like planets are common, it seems logical to assume that some would develop life, and eventually intelligent life. The Drake equation offers a method to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Formulated by astronomer Frank Drake in 1961, it multiplies several factors including the rate of star formation, the fraction of those stars with planets, the number of habitable planets per solar system, the likelihood of life arising, the chance of that life being intelligent, the probability of technological civilizations, and the lifespan of such civilizations. While each factor involves significant uncertainties, the equation highlights the potential for numerous civilizations. However, this theoretical abundance clashes with the lack of empirical evidence, emphasizing the Fermi paradox. The Drake equation, combined with our expanding knowledge of exoplanets, suggests that we should have encountered some sign of extraterrestrial intelligence by now. Yet the cosmos remains eerily quiet. The enormity of the universe is a fundamental element in understanding the Fermi paradox. Current scientific consensus places the age of the universe at around 13.8 billion years. This vast time span has allowed for the development and evolution of countless celestial objects and potentially life forms. Astronomers estimate that the observable universe contains upwards of 2 trillion galaxies, each housing billions of stars. This staggering number is derived from deep space observations, particularly from the Hubble Space Telescope, which has peered into distant parts of the universe, revealing galaxies of various sizes and types. Within these galaxies, the number of stars is almost incomprehensible. For instance, our Milky Way galaxy alone contains an estimated 100 to 400 billion stars. Extending this to the entire universe, the total number of stars reaches an almost inconceivable number. Each star potentially hosts a system of planets, increasing the likelihood of habitable environments. The scale of the universe suggests that the formation of Earth-like planets is not unique. Observations and models indicate that a significant fraction of stars might have planets in their habitable zones, regions where conditions could allow for liquid water, a prerequisite for life as we know it. This realization has been bolstered by the discovery of exoplanets, some of which orbit within these habitable zones. The concept of habitable zones, often referred to as the Goldilocks zone, is crucial in the search for extraterrestrial life. These zones are the regions around a star where conditions might be just right, not too hot and not too cold, for liquid water to exist on a planet's surface. The importance of liquid water cannot be overstated, as it's a key ingredient for life as we know it. With advancements in space technology, particularly the deployment of space telescopes like Kepler and TESS, we have begun to identify planets that lie within these habitable zones. These discoveries have significantly increased the estimated number of potentially habitable planets in our galaxy and beyond. However, the existence of a habitable zone does not guarantee life. Other factors, such as planetary atmosphere, magnetic field, geological activity, and chemical composition, play crucial roles in determining a planet's habitability. The diversity of planets observed so far shows a wide range of environments, from gas giants to rocky worlds, each with unique conditions. The Drake equation is a probabilistic formula used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Proposed by astronomer Frank Drake in 1961, it multiplies several variables to arrive at an estimation. The Drake equation includes the following variables. The rate of formation of stars is suitable for the development of intelligent life. The fraction of those stars with planetary systems, the number of planets per solar system with an environment suitable for life, the fraction of suitable planets on which life actually appears, the fraction of life-bearing planets on which intelligent life emerges, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space, the length of time such civilizations release detectable signals into space. Each of these variables involves significant uncertainties and is subject to ongoing research and debate. For example, the rate of star formation can be estimated based on observations, but the fraction of those stars with planetary systems, and further, the number with habitable planets, is less clear. Similarly, the emergence of life, let alone intelligent life, and the development of technology capable of signaling to the cosmos are deeply uncertain. The application of the Drake equation has resulted in a wide range of estimates, from a pessimistic view of a lonely universe to a universe teeming with civilizations. Early applications suggested optimistic numbers, but as our understanding of each variable has evolved, so too have the estimates. Recent astronomical discoveries, especially of exoplanets, have provided more data, particularly for the first few variables of the equation. The discovery of numerous Earth-like planets in habitable zones suggests that suitable environments for life might be common. However, the latter variables, particularly those involving the emergence and longevity of intelligent, communicative civilizations, remain highly speculative. Given these uncertainties, current estimates range widely. Some scientists propose that intelligent life might be rare, pointing to the unique circumstances and coincidences that led to life on Earth. Others argue for a more abundant universe, with many civilizations existing but perhaps separated by vast distances and timescales, making communication and detection unlikely. The hypotheses for the Fermi Paradox attempt to explain the discrepancy between the high probability of extraterrestrial civilizations and the lack of evidence for or contact with such civilizations. These hypotheses explore a range of scenarios from the development and behavior of intelligent life to the technological and physical limitations of detection and communication. The exploration of these hypotheses is crucial in understanding the paradox and guiding future research and exploration efforts in the search for extraterrestrial life. The rare Earth hypothesis posits that Earth-like planets with conditions conducive to life are exceptionally rare in the universe. This hypothesis contrasts with the previously more optimistic view that habitable planets might be common. It suggests that a multitude of highly specific and often interdependent conditions are necessary for complex life to evolve, making such occurrences exceedingly rare. Earth boasts a unique combination of factors that have been crucial for the development and sustenance of life. These include its position in the habitable zone of the Sun, a stable climate, a protective magnetic field, plate tectonics, and the presence of water in its liquid form. Additionally, Earth's large moon plays a significant role in stabilizing the planet's axial tilt, which is critical for a stable climate. The rare Earth hypothesis argues that this combination of factors is not only beneficial, but also necessary for complex life. For example, the presence of Jupiter in our solar system is thought to shield Earth from frequent catastrophic asteroid impacts, which could otherwise inhibit the development of complex life forms. Moreover, Earth's long evolutionary history, which allowed for the gradual development of biodiversity, may also be a rare occurrence. While exoplanet discovery has confirmed that planets exist in the habitable zones of their stars, the probability of finding another planet with Earth's unique set of life-supporting conditions is uncertain. Factors like a planet's size, composition, atmosphere, orbital stability, and the characteristics of its host star all contribute to its habitability. The rare Earth hypothesis maintains that the precise conditions necessary for life are so specific and complex that even planets within habitable zones may not necessarily harbor life. For example, the right chemical composition is needed for a breathable atmosphere, and specific geophysical processes are required to maintain it. Moreover, the evolution of intelligent life as seen on Earth might depend on an even narrower set of circumstances. Consequently, even if habitable planets are relatively common, those supporting complex or intelligent life could be exceedingly rare. The Great Filter concept addresses the paradox by proposing that there is a stage, or multiple stages, in the evolution of life that is extremely hard to pass through. This filter could explain why we haven't encountered evidence of extraterrestrial civilizations. The filter might lie in the past, suggesting that the emergence of life or its evolution to intelligence is exceedingly rare. Or it could be in the future, implying a looming challenge that prevents civilizations from enduring or expanding. The Great Filter is a term used to describe hypothetical stages in the evolution of life that are difficult to surpass. These stages could range from the emergence of life from non-life, abiogenesis, the development of multicellular organisms, the rise of intelligence and tool-using civilizations, to the ability to communicate across interstellar distances. This hypothesis implies that if the filter is behind us, then the emergence of life, or at least complex life, is an extremely rare event in the universe. If the filter lies ahead, it suggests a future hurdle that prevents civilizations from lasting long enough to make interstellar contact, such as self-destruction through war or environmental catastrophe. Possible past filters include the transitions from simple to complex cells, the development of sexual reproduction, which increases genetic diversity, or the leap from unicellular to multicellular life. Each of these stages represents a significant evolutionary leap and might be exceedingly rare in the universe. Future filters could involve the sustainability of technological civilizations. This includes the potential for self-destruction through nuclear war, environmental degradation, or other self-inflicted catastrophes. Another possibility is that technological civilizations might tend to evolve or develop in ways that make them undetectable or uninterested in communication with others. This hypothesis considers the limitations of our current technology in detecting extraterrestrial life and the possibility that advanced civilizations may have sociological characteristics or technologies beyond our comprehension or detection capabilities. Our current technological limitations significantly impact our ability to detect signs of extraterrestrial life. This includes limitations in the range and sensitivity of our telescopes and the challenges in interpreting the signals we do receive. For example, we are currently only able to detect a very small fraction of the electromagnetic spectrum, and our radio telescopes have a limited range. Additionally, there is the question of what kind of signals we should be looking for. Civilizations might use communication technologies far advanced from our radio and optical signals, making their communications undetectable to us. Furthermore, the vast distances of space mean that any signals we detect would be from the distant past, potentially from civilizations that no longer exist. Advanced civilizations may have sociological or behavioral characteristics that make them undetectable or uninterested in contacting us. They might choose to isolate themselves, either for ethical reasons, non-interference, or out of fear of potential threats. There is also the possibility that they have moved beyond physical form or have developed in ways that are beyond our understanding or detection capabilities. The challenges in communicating with and detecting extraterrestrial life are multifaceted, involving technological, physical, and theoretical limitations. These challenges impact our search strategies and influence the interpretations of the results, or lack thereof, from SETI initiatives and other observational efforts. Understanding these challenges is crucial for refining our search methods and developing new technologies to enhance our chances of discovering extraterrestrial life. The quest to detect extraterrestrial intelligence is hindered by significant technological limitations. Current technologies face challenges in both detecting signals from other civilizations and sending messages over vast distances of space. The primary challenge in long-distance communication with potential extraterrestrial intelligence is the immense distances involved. Signals, even traveling at the speed of light, would take years to travel between stars. For instance, a signal from the nearest star system, Alpha Centauri, would take over 4 years to reach Earth. This time lag makes real-time communication impractical. Moreover, signals weaken with distance, becoming harder to distinguish from the cosmic background noise. The technology required to send a strong, focused signal over such distances is beyond our current capabilities. Likewise, detecting a signal from a distant civilization would require immense sensitivity and precision. Additionally, there is the question of what form such a communication would take. Civilizations could use different parts of the electromagnetic spectrum, or even entirely different communication methods, like neutrinos or gravitational waves, which we are currently ill-equipped to detect or interpret. Current telescopes and space probes are limited in their range and sensitivity, which hampers our ability to detect signs of extraterrestrial life. Radio telescopes like the Arecibo Observatory, before its collapse, and the Green Bank Telescope can only detect signals of certain strengths and frequencies. Optical telescopes are limited in their ability to discern small, potentially habitable planets around distant stars. Space probes, such as the Voyager and Pioneer missions, have only just reached the outer boundaries of our solar system. The vast distances of interstellar space make it impractical, with current technology, to send probes to other star systems within a human lifetime. There is also a limitation in our understanding of what to look for. Our search has been primarily focused on Earth-like conditions and radio signals, which may not be indicative of all forms of extraterrestrial intelligence. The search for extraterrestrial intelligence, SETI, is an ongoing effort to detect intelligent life outside Earth. It involves monitoring electromagnetic signals for signs of transmissions from alien civilizations. This scientific endeavor has evolved significantly over the years, incorporating more sophisticated technology and broader search parameters. SETI projects have varied in scope and methodology. The early days of SETI saw projects like Project Ozma, which in 1960 used a radio telescope to listen for signals from 2 nearby stars. Although it did not find alien signals, it set a precedent for future searches. In more recent years, projects have become more comprehensive. The SETI Institute's Allen Telescope Array is designed to continuously scan the skies. Similarly, the Breakthrough Listen project, launched in 2015, is one of the most ambitious efforts, utilizing powerful telescopes to survey the million closest stars, the galactic plane, and the nearest galaxies. SETI efforts have also included sending messages into space, like the Arecibo message in 1974, a digital encoding of basic information about humanity and Earth sent towards a star cluster. The future of SETI is likely to see an increase in sensitivity, range, and speed of detection methods. Upcoming telescopes like the Square Kilometer Array will offer unprecedented sensitivity and the ability to scan large swaths of the sky more quickly. There is also a growing interest in new types of signals, such as laser pulses or non-radio wavelengths. Technological advancements may enable the detection of subtle signs of extraterrestrial technology, like waste heat emissions or artificial light. Artificial intelligence and machine learning are also becoming crucial in SETI. These technologies can process vast amounts of data more quickly and effectively than humans, potentially identifying patterns or signals that might otherwise be missed. The search for extraterrestrial intelligence is not just a scientific endeavor, but also raises profound philosophical and ethical questions. These include considerations about our place in the universe, the nature of intelligence and life, and the potential implications of contact with another civilization. Delving into these aspects helps us understand the broader significance of SETI and prepares us for the potential outcomes of this quest. The Anthropic principle is a philosophical consideration that provides a framework for understanding the universe's properties in relation to the existence of human life. It suggests that the universe's physical laws and constants are finely tuned in a way that allows for the emergence and evolution of conscious beings, like humans. Essentially, it implies that the universe must be compatible with the conscious beings that observe it. The Anthropic principle comes in various forms, but at its core, it addresses why the fundamental physical constants of the universe are conducive to the development of life. This principle is relevant in discussions about the Fermi Paradox and the search for extraterrestrial life because it touches on the probability of life existing elsewhere in the universe. One interpretation, the weak Anthropic principle, posits that we observe these particular universal conditions simply because they are the ones that allow us to exist. In contrast, the strong Anthropic principle suggests that the universe is somehow compelled to develop life-conscious beings. The relevance of this principle in astrobiology and SETI is significant. It raises the question of whether our universe is uniquely suited for life, or if these conditions are merely a cosmic coincidence. This principle also intersects with the fine-tuning argument in cosmology, which proposes that the universe's constants are precisely balanced for life to exist. The Anthropic principle has profound implications for our understanding of the universe. If the universe is fine-tuned for life, does that imply the existence of multiple universes or a multiverse where different physical laws apply? This leads to the multiverse theory, suggesting that our universe is just one of many, each with its own set of physical laws. In the context of the Fermi Paradox, the Anthropic principle could imply that while our universe permits life, the specific conditions for intelligent life may be exceedingly rare. This rarity could be an explanation for why we have not yet encountered extraterrestrial civilizations. Furthermore, the principle challenges the notion of a human-centric universe, pushing us to consider broader cosmological perspectives. It invites debate on whether our existence is a product of random chance or a deeper cosmological necessity. The search for and potential contact with extraterrestrial intelligence carries significant ethical implications. These encompass the responsibility we have in making contact, the potential risks and benefits of such contact, and the broader impact on human philosophy and society. The act of attempting to contact alien life forms raises questions about the ethical responsibility of humanity. One concern is the potential impact on extraterrestrial civilizations. Are we morally obligated to avoid potentially harmful interference with other life forms? This question becomes especially pertinent in light of our own history, where contact between civilizations with differing levels of technology often resulted in negative outcomes for the less advanced society. Another aspect of this responsibility is the debate over active SETI, where messages are deliberately sent into space as opposed to passive SETI, which only listens for signals. Some argue that actively reaching out could expose Earth to unknown risks from advanced civilizations. There's an ongoing debate within the scientific community about the wisdom and safety of transmitting messages into space. The discovery of extraterrestrial intelligence would have profound implications for human philosophy and society. It would challenge many fundamental aspects of human belief systems, including religion, the uniqueness of humanity, and our place in the universe. Such a discovery could lead to a paradigm shift in our understanding of life and intelligence. It might prompt us to reconsider what it means to be intelligent or conscious, and could lead to new philosophical and ethical considerations about our relationship with other forms of life. On a societal level, The discovery could impact international relations, as humanity would need to present a united front in the face of extraterrestrial contact. It could also lead to new collaborations and a more global perspective, overcoming terrestrial divisions in recognition of our shared status as inhabitants of Earth. Exploring alternative explanations and theories helps broaden our understanding of the Fermi Paradox and the potential reasons behind the apparent silence of the universe. These theories and explanations provide different perspectives and possibilities, contributing to the ongoing debate and research in the field. The zoo hypothesis proposes a reason for the lack of contact with extraterrestrial civilizations. They know about us, but have chosen not to contact us. This hypothesis suggests that advanced civilizations are deliberately avoiding contact with Earth to allow for natural evolution and sociocultural development, much like zookeepers trying to prevent animals from being disturbed by human presence. The zoo hypothesis, first proposed by John A. Ball in 1973, posits that Earth and human society are being observed by advanced extraterrestrial civilizations, but these civilizations have established a sort of galactic quarantine around us. This quarantine is maintained to ensure that human development proceeds without outside interference, allowing for an unaltered natural progression of our species and culture. According to this hypothesis, these advanced civilizations might be monitoring us in a way that is undetectable with our current technology. They might be waiting for a certain level of technological, social, or moral development before they make contact. This idea aligns with the principle of non-interference, a common theme in science fiction, where more advanced civilizations avoid influencing the development of less advanced ones. The zoo hypothesis raises several ethical and philosophical questions. It challenges our understanding of autonomy and free will, as it suggests that our development might be subject to the whims of more advanced beings. There are also ethical considerations regarding the right of a more advanced civilization to observe and potentially experiment on a less advanced one without its knowledge or consent. Philosophically, this hypothesis touches on themes of existentialism and anthropocentrism. It forces us to confront the possibility that we might not be the most advanced form of life, and that our perception of the universe might be limited or skewed. It also raises questions about our significance in the grand scheme of the cosmos. Other speculative theories offer diverse explanations for the Fermi Paradox. These include the Transcension hypothesis, which suggests a post-biological future for intelligent life, and theories about parallel universes or a multiverse, which propose that extraterrestrial life might exist in dimensions or universes separate from our own. The Transcension hypothesis, proposed by John Smart, suggests that advanced civilizations do not expand outward, but rather inward, effectively transcending into a black hole-like condition. This hypothesis posits that as civilizations advance, they miniaturize and internalize their technology, eventually reaching a point where they are no longer detectable by external observers. This inward journey might involve the creation of highly advanced, compact, and efficient technologies that operate on microscopic or even Planck scales. Such a civilization would be focused on information processing and virtual realities, possibly transcending physical spacetime as we understand it. The concept of parallel universes and the multiverse arises from various interpretations of quantum mechanics and cosmology. These theories propose that our universe is just one of many, potentially infinite universes, each with its own physical laws and constants. In the context of the Fermi Paradox, these theories suggest that extraterrestrial civilizations might exist in these other universes, which would be fundamentally inaccessible to us. This could explain the silence we observe. We are not just separated by space, but by the very fabric of reality. The exploration of the Fermi Paradox, from its foundational concepts to the various hypotheses and theories proposed to explain it, provides a comprehensive view of our current understanding and the ongoing debates in this field. These discussions not only enrich our knowledge about the potential for extraterrestrial life, but also offer profound insights into our place in the cosmos, the nature of life and intelligence, and the future of human exploration and understanding. The Fermi Paradox arises from the contradiction between the high probability of extraterrestrial civilizations, as suggested by the vast number of stars and galaxies, and the complete lack of evidence for or contact with such civilizations. It encompasses various hypotheses and theories, each offering potential explanations for this apparent silence in the cosmos. The rare Earth hypothesis suggests that Earth-like conditions may be exceptionally rare, making the emergence of life similarly uncommon. The Great Filter theory proposes that there is a stage in the evolution of life that is extremely difficult to pass, which could explain the absence of detectable extraterrestrial civilizations. The zoo hypothesis posits that advanced civilizations are aware of us, but choose to avoid contact, maintaining a galactic quarantine for the sake of our natural development. Technological limitations in detection and long-distance communication also play a significant role in this paradox. Current technologies, including telescopes and space probes, are limited in their range, sensitivity, and the types of signals they can detect. The search for extraterrestrial intelligence, SETI, has evolved over the years, but it still faces these fundamental challenges. The future of research and discovery in addressing the Fermi Paradox looks promising, with advancements in technology and methodology. Increased sensitivity and range of telescopes, both ground-based and in space, will enhance our ability to detect signals and observe exoplanets. Projects like the James Webb Space Telescope and the Square Kilometre Array will provide deeper insights into the universe, potentially identifying more habitable planets and the signs of life. Artificial intelligence and machine learning are expected to play a crucial role in analyzing the vast amounts of data collected by these projects. These technologies could identify patterns or signals that might otherwise be overlooked. The Fermi Paradox is more than a scientific query. It is a profound philosophical and existential question. It challenges us to think about our place in the universe, the uniqueness of Earth and human life, and the nature of intelligence and civilization. The paradox encourages a multidisciplinary approach, combining astronomy, biology, philosophy, and technology to explore these fundamental questions.